In this video, we'll formulate the definition of the derivative of a function by talking about relieving knee pain. Here are the main points that will be addressed in the video. Please read this and think about them carefully as you watch the video. The derivative of a function f at an input value x equals a is the limit of an average rate of change of f of x with respect to x over the time interval a, a plus h, assuming h is greater than 0 as h approaches 0. The derivative of a function f at an input value x equals a is given by either of the following expressions. Limit as h approaches 0 of the expression f of a plus h minus f of a over h. Limit as x approaches a of expression f of x minus f of a over x minus a. Let's think about the scenario where a person takes 400 milligrams of ibuprofen. In this case, the function f of t equals 400 times 0.71 to the t represents the amount of ibuprofen in the body in milligrams in terms of the number of hours elapsed since taking the 400 milligram dose. A question we might be interested in is how quickly is ibuprofen leaving the body 4 hours after being administered. To help us think about the scenario, let's make a graph of our function. We'll have the horizontal axis be elapsed time in hours since the ibuprofen was taken, and the vertical axis be the amount of ibuprofen in milligrams. Now let's draw the graph of f of t. We see that at 4 hours, the amount of ibuprofen remaining in the body is about 101.6 milligram. We can also see this on the graph. Next, we need to try to approximate the instantaneous rate of t equals 4 by computing an average rate over a time interval starting at t equals 4 hours. In this scenario, the average rate is a change in amount of ibuprofen per a change in time. To start, we'll use a 3-hour change in time. On the graph, delta t can be represented by the length of a red arrow from the point on the function at time 4. Here, delta t is 3. Delta f will be the corresponding length of this blue arrow, which we would compute by subtracting f evaluated 4 from f evaluated 7. So the average rate is the change in the values of the function divided by 3. Since we have a formula for f, we can evaluate the function at t equals 7 and t equals 4, compute the difference, and divide. This gives us an average rate of negative 21.755 milligrams per hour. This computation would give us an accurate measure of the rate of change if the rate were constant over the 3-hour time interval. However, this isn't the case. So this is not a very precise approximation of the instantaneous rate of change. However, we can make this approximation more precisely by making the interval of time smaller. Let's begin by making delta t smaller. Say delta t is 2. We can again calculate the average rate of change by dividing the change in f by change in t. So when delta t is 2 hours, the average rate of change was negative 25.20 milligrams per hour. Let's zoom in a little bit to see this better. We'll keep this image on the screen to compare with some other approximations. Now, let's look at what would happen if we used a smaller delta t. Here, delta t equals 1. We can compute the average rate of change over this interval by dividing the change in f by change in t. So delta t is 1 hour. The average rate change is negative 29.48 milligrams per hour. Let's zoom in a little bit to see this better. We'll keep this image on the screen to compare with some other approximations. Now let's look at what will happen if we use a smaller delta t. Here, delta t equals 1/2, or 0.5. We can again compute the average rate of change over this interval by dividing the change in f by change in t. So when delta t is 1/2 hour, the average rate is negative 32 milligrams per hour. Let's zoom in a little bit to see this better on the graph. And then keep this image on the screen. Then we could use a smaller delta t, say 1/4 or 0.25. This would give us an average rate of 33.36 milligrams per hour. And we'll save this picture. Then we could use an even smaller delta t, say 1/10, 0.1. This would give us an average rate of negative 34.22 milligrams per hour. And we'll save this picture. And now we have 5 graphs we can compare. From top to bottom, we can see that how the amount of change in time was decreasing from 2 hours to 1 hour to a half to a quarter and to a tenth of an hour. Let's take a look at the graphs. In our first graph with delta t of 2 hours, we can see that graph is curved. So the slope, and therefore rate at which ibuprofen is leaving the body, is changing over a 2-hour interval. When we use delta t of a 1 hour, the slope was changing over the interval. And the same was true when we used delta t of a half hour. However, when we use a delta t of a quarter hour, the slope starts to look constant. And with a delta t of tenth of an hour, the slope looks nearly constant over the time interval. So the ibuprofen is close to leaving the body at a constant rate. What would we see if we continue this process? When we use the delta t of 1/100th of an hour, the average rate at which ibuprofen is leaving the body is negative 34.754 milligrams per hour. When we use delta t of 1/1000th of an hour, the average rate at which ibuprofen is leaving the body is negative 34.807 milligrams per hour. When we use delta t of 1/10,000th of an hour, the average rate at which ibuprofen is leaving the body is negative 34.8128 milligrams per hour. When we use delta t of 100,000th of an hour, the average rate of change at which ibuprofen is leaving the body is negative 34.813 milligrams per hour. So as we make the time interval smaller, these average rates of change appear to be getting closer to a particular number, roughly negative 34.813 milligrams per hour. To summarize what we have observed, as we look at shorter and shorter time intervals, the graph of f of t looks more and more like a straight line. It is getting closer to having a constant rate of change. As this happens, the successive average rates of change are getting closer to a particular number. In more formal notation, we write f of 4 plus delta t minus f of 4, all divided by delta t, to show the average rates of change. We write delta t goes to 0 to represent the decreasing length of the time intervals. And we write the limit to indicate the number of these are getting closer to. It is important to remember that the average rate of change in this scenario requires that there be a change in time. So the limit isn't itself an average rate of change. It's a number that the average rates of change are approaching. From our work, we saw that these average rates of change were getting closer to roughly negative 34.813 milligrams per hour. This limiting value, which we write as f prime of 4, is the instantaneous rate of change of f of t with respect to t at t equals 4 hours, which also we call the derivative of f at t equals 4.